Okay, so in this video, we will look at an example of a so-called telescoping series. Now, telescoping series are a special class of series that not only can be shown to be convergent, but also can be evaluated exactly. So this will be such an example. So we will show not only that this series converges, so returns a real number, but we will find the exact real numbers that the series converges to. As always, to get a feeling of what kind of numbers we're adding, we can expand the series out and look at the first few terms. So we're summing 1 over n squared plus 2n, when n begins at 1 and goes all the way up to infinity. So when n is 1, we have 1 over 1 squared is 1 plus 2 times 1, 2. 1 plus 2 is 3. So 1/3 plus. Then n is 2. 2 squared is 4 plus 2 times 2, 4. 4 plus 4 is 8, so it's 1 over 8. Plus when n is 3, we get 9 plus 6, 15. Plus when n is 4, we get 16 plus 8, 24. Let's look at one more. When n is 5, 25 plus 10, 35. So here are the first 5 terms of this infinite series, and now we are going to show that this series does converge if we add all of these rational numbers. This infinite sum returns an actual real number, and we're going to do even more. We'll ask, what is the exact value of this infinite series? To do so, we will have to look at the partial sum. So we'll have to be rigorous here. So if you recall, the rigorous way of evaluating an infinite series is to first consider the partial sum. So we will sum 1 over n squared plus 2n as n goes from 1 to a fixed point, uppercase n. So here we are summing the first uppercase n terms of the infinite series. And of course, to go from the finite sum to the series, we have to let the upper bound of summation approach infinity. And the idea when you deal with telescoping series is there is a really clever way, and we're going to call this Sn, the sum of the first uppercase n terms of the infinite series. There is a very clever way of simplifying this expression so that almost all the terms cancel out, and you're left in the end with very few terms. And this is the meaning of the word telescoping, which means that if you play your cards right, almost everything will cancel out, which will greatly simplify this summation. What's interesting here is that to do so, to simplify the partial sum, we have to use our knowledge of partial fractions. So let's look at the terms that we're summing. 1 over n squared plus 2n. We can factor in n. This is 1 over n times n plus 2. And now we can try to decompose this rational expression, 1 over n times n plus 2, into a sum of two partial fractions. Some constant over n plus some constant over n plus 2. And this is again the idea of decomposing a rational function, here a rational function of n, into a sum of partial fractions. We can then multiply by n times n plus 2 on both sides of the equality, which will show that 1 is equal to a over n times n plus 2. These will cancel, so a times n plus 2. Plus b over n plus 2 times n plus 2. These will cancel, so b times n. And if you want here, you can combine the multiple of n, so this would be n times a plus b plus the constant term 2a. Well, the constant term here is 1, so 2a must be 1. Therefore, a must be 1 over 2. A plus b is the multiple of n. There is no n here, so the multiple of n must be 0. If a plus b is 0, b is negative a, therefore b is negative 1/2. And with this now, we are ready to simplify the partial sum. So we'll go over to Sn. And instead of writing 1 over n squared plus 2n, we will write its partial fraction decomposition, because this expression is 1/2 over n minus 1/2 over n plus 2. Okay, so now where do we go from here? The idea is, as we have a finite sum, we can split up the sum into two sums, the sum of these minus the sum of these, and as we expand out both sums, we will see where the cancellation takes place. So this is, and I will do two things at once here, so I can sum these terms first, but as 1/2 is a constant multiple with respect to n, I can factor 1/2 outside, so it's 1/2 times the sum from 1 to n of 1 over n, minus, I can factor this 1 out as well, but as 1/2 is a multiple of both series, both sum I should say, we can factor it out of the two sums. So imagine factoring 1/2 outside, and now we're left with the sum of 1 over n, check, minus the sum of 1 over n plus 2. And this actually is fantastic. It may not be clear as is, but if we simply expand both, you will see why this is so nice. One other comment. Look at your denominators. It is n and n plus 2. There's a difference of 2 between the two denominators. So since we have a difference of 2, the key point to see the cancellation fully, we have to write out the first 3 terms, 2 plus 1 terms of each sum, and the last 3 terms of each sum as well. If the term here was, say, n plus 5, and here this was n plus 1, there would be a difference of 4, and so we would write the first 5 terms of each sum and the last 5 terms of each sum. And this will allow you to see the cancellation fully. So let's do so. The first sum, we're summing 1 over n from 1 to uppercase n, so the first 3 terms are clearly 1 plus 1/2 plus 1/3 plus dot dot dot, and the last 3 terms. Well, the last term is 1 over uppercase n. If we go back one step, it's 1 over uppercase n minus 1. Go back one step, 1 over uppercase n minus 2. So the first 3 terms of this sum, the last 3 terms of this sum, minus the exact same thing for the other sum. We're summing 1 over n plus 2. N begins at 1, so we get 1 over 1 plus 2, 1 over 3. So it's 1 over 3 plus 1 over 4 plus 1 over 5 plus dot dot dot. The last 3 terms. Well, the sum ends at 1 over uppercase n plus 2. If we go back one step, 1 over uppercase n plus 1. Go back one other step, 1 over uppercase n. And now, the cancellation should be apparent. Look at the overlap between the first sum and the second sum. It begins here at 1 over 3. 1 is not here. 1/2 is not here, but 1/3 is. So we have 1/3 minus 1/3, this will cancel. Plus 1/4 minus 1/4, this will cancel. Plus 1/5 minus 1/5, this will cancel, all the way up to 1/n minus 1/n. So this will cancel with this. They are the exact same sums. We do this sum minus itself. So it simply goes to 0. And now we're left with only 4 terms. The first 2 terms of the first sum, so 1 plus 1/2, all of these terms cancel, and then don't forget minus 1/n plus 1 minus 1/n plus 2. And why is this fantastic? Well, if you think of the original partial sum, Sn, we are summing uppercase n integers, 1/3 plus 1/8 up to 1 over uppercase n squared plus 2 times uppercase n. So as n gets bigger and bigger and bigger, we are summing more and more and more terms. So Sn becomes more and more complicated. But not with this form. No matter how large n is, we only ever have 4 terms. And with this now, we can evaluate the exact value of this infinite series, as the exact value of the infinite series is the limit as n goes to infinity of Sn. And now with our simplified form of Sn, we will have a trivial limit. So let's go back from almost the beginning. When you have an infinite series, you first look at if we are being rigorous, the partial sum. So summing from 1 to uppercase n, and then of course letting uppercase n tend to infinity, just as we do for improper integrals. But this is nothing other than what we called Sn, the partial sum. And now of course we will replace Sn by its simplified expression. Here we'll add 1 plus 1/2, which is 3/2, minus 1/n plus 1, minus 1/n plus 2. And this limit now is trivial. As n goes to infinity, 1/n plus 1 shrinks to 0, 1/n plus 2 shrinks to 0, and so we're left with 1/2 times 3/2, which is simply 3/4. And we're done. So this infinite series does converge, and it converges to the exact value of 3/4. And so we can go back and say, well, here are the first few terms of this infinite series, and if we add all of these terms, this infinite list of real numbers, the answer is now no longer unknown, but is exactly 3/4, which is far from obvious, but there it is. So every time you sum terms that are of the form 1 over some kind of rational function in terms of n, if you can decompose the terms you're summing into a sum of partial fractions, usually by expanding out the two finite sums, you will be able to see a huge cancellation taking place, and then with the simplified form of the partial sum, you should be able to easily find the limit and obtain the exact value of the power of the series. And that's it.